For an elementary calculus-based introduction, see Divergent series on Wikiversity Les séries divergentes sont en général quelque chose de bien fatal c'est une honte qu'on ose fonder aucune. Demonstration. Wright, H. Abel, Letter to Hombo, January 1826, reprinted in Volume 2 of his collected papers. In mathematics, a divergent series is an infinite series that is not convergent, meaning that the infinite sequence of the partial sums of the series does not have a finite limit. If a series converges, the individual terms of the series must approach zero. Thus, any series in which the individual terms do not approach zero diverges. However, convergence is a stronger condition. Not all series whose terms approach zero converge. A counterexample is the harmonics series. The divergence of the harmonics series was proven by the medieval mathematician Nicole Osmer. In specialized mathematical contexts, values can be objectively assigned to certain series whose sequence of partial sums diverges. This is to make meaning of the divergence of the series. A summability method or summation method is a partial function from the set of series to values. For example, Cesaro summation assigns Grandi's divergent series the value 1/2. Cesaro summation is an averaging method, in that it relies on the arithmetic mean of the sequence of partial sums. Other methods involve analytic continuations of related series. In physics, there are a wide variety of summability methods. These are discussed in greater detail in the article on regularization. History. Before Cauchy, mathematicians asked not, how shall we define 1 minus 1 plus 1, but, what is 1 minus 1 plus 1, and that this habit of mind led them into unnecessary perplexities and controversies which were often really verbal. Thumb, H. Hardy, Divergent Series, page 6. Before the 19th century, divergent series were widely used by Euler and others, but often led to confusing and contradictory results. A major problem was Euler's idea that any divergent series should have a natural sum, without first defining what is meant by the sum of a divergent series. Cauchy eventually gave a rigorous definition of the sum of a series, and for some time after this, divergent series were mostly excluded from mathematics. They reappeared in 1886 with Poincaré's work on asymptotic series. In 1890, Cesaro realized that one could give a rigorous definition of the sum of some divergent series, and defined Cesaro summation. In the years after Cesaro's paper, several other mathematicians gave other definitions of the sum of a divergent series, though these are not always compatible. Different definitions can give different answers for the sum of the same divergent series. So when talking about the sum of a divergent series, it is necessary to specify which summation method one is using. Theorems on methods for summing divergent series. A summability method M is regular if it agrees with the actual limit on all convergent series. Such a result is called an abelian theorem for M, from the prototypical Abel's theorem. More interesting and in general more subtle are partial converse results, called Tauberian theorems, from a prototype proved by Alfred Tauber. Here partial converse means that if M sums the series sigma, and some side condition holds, then sigma was convergent in the first place. Without any side condition, such a result would say that M only summed convergent series. The operator giving the sum of a convergent series is linear, and it follows from the Hahn-Banach theorem that it may be extended to a summation method summing any series with bounded partial sums. This fact is not very useful in practice since there are many such extensions, inconsistent with each other. And also since proving such operators exist requires invoking the axiom of choice or its equivalents, such as Zorn's lemma. They are therefore non-constructive. The subject of divergent series, as a domain of mathematical analysis, is primarily concerned with explicit and natural techniques such as Abel's summation, Cesaro summation, and Borel summation, and their relationships. The advent of Wiener's Tauberian theorem marked an epoch in the subject, introducing unexpected connections to Banach algebra methods in Fourier analysis. Summation of divergent series is also related to extrapolation methods and sequence transformations as numerical techniques. Examples for such techniques are Padé approximants, Levin-type sequence transformations, and order-dependent mappings related to renormalization techniques for large-order perturbation theory in quantum mechanics. Properties of summation methods. Summation methods usually concentrate on the sequence of partial sums of the series. While this sequence does not converge, we may often find that when we take an average of larger and larger numbers of initial terms of the sequence, the average converges, and we can use this average instead of a limit to evaluate the sum of the series. So in evaluating A equals A0 plus A1 plus A2 plus, we work with the sequence S, where S0 equals A0 and Sn plus 1 equals Sn plus n plus 1. In the convergent case, the sequence S approaches the limit A. A summation method can be seen as a function from a set of sequences of partial sums to values. If A is any summation method assigning values to a set of sequences, we may mechanically translate this to a series summation method A sigma that assigns the same values to the corresponding series. There are certain properties it is desirable for these methods to possess if they are to arrive at values corresponding to limits and sums, respectively. Regularity. A summation method is regular if, whenever the sequence S converges to X, A equals X. Equivalently, the corresponding series summation method evaluates A sigma equals X. Linearity. Since the terms n plus 1 equals Sn plus 1 minus Sn of the series are linear functionals on the sequence S and vice versa, this is equivalent to A sigma being a linear functional on the terms of the series. Stability. If S is a sequence starting from S0 and S is the sequence obtained by omitting the first value and subtracting it from the rest, so that Sn equals Sn plus 1 minus S0, then A is defined if and only if A is defined, and A equals S0 plus A. Equivalently, whenever An equals n plus 1 for all n, then A sigma equals A0 plus A sigma. Another way of stating this is that the shift rule must be valid for the series that is summable by this method. The third condition is less important, and some significant methods, such as Borel summation, do not possess it. One can also give a weaker alternative to the last condition: finite reindexability. If A and A are two series such that there exists a bijection such that I equals AF for all I, and if there exists some such that I equals AI for all I greater than n, then A sigma equals A sigma. Note that this is a weaker condition than stability, because any summation method that exhibits stability also exhibits finite reindexability. But the converse is not true. A desirable property for two distinct summation methods A and B to share is consistency. A and B are consistent if for every sequence S to which both assign a value, A equals B. If two methods are consistent, and one sums more series than the other, the one summing more series is stronger. There are powerful numerical summation methods that are neither regular nor linear. For instance, nonlinear sequence transformations like Levin-type sequence transformations and Padé approximants, as well as the order-dependent mappings of perturbative series based on renormalization techniques. Taking regularity, linearity and stability as axioms, it is possible to sum many divergent series by elementary algebraic manipulations. This partly explains why many different summation methods give the same answer for certain series. For instance, whenever R1, the geometric series can be evaluated regardless of convergence. More rigorously, Any summation method that possesses these properties and which assigns a finite value to the geometric series must assign this value. However, when R is a real number larger than 1, the partial sums increase without bound, and averaging methods assign a limit of infinity. Classical summation methods. The two classical summation methods for series, ordinary convergence and absolute convergence, define the sum as a limit of certain partial sums. Strictly speaking, these are not really summation methods for divergent series, as by definition a series is divergent only if these methods do not work, but are included for completeness. Most but not all summation methods for divergent series extend these methods to a larger class of sequences. Absolute convergence. Absolute convergence defines the sum of a sequence of numbers to be the limit of the net of all partial sums at 1 plus ac. If it exists, it does not depend on the order of the elements of the sequence. And a classical theorem says that a sequence is absolutely convergent if and only if the sequence of absolute values is convergent in the standard sense. Sum of a series. Cauchy's classical definition of the sum of a series A0 plus A1 plus defines the sum to be the limit of the sequence of partial sums A0 plus n. This is the default definition of convergence of a sequence. Norland means. Suppose Pn is a sequence of positive terms, starting from P0. Suppose also that if now we transform a sequence S by using P to give weighted means setting, then the limit of Tennessee as on goes to infinity as an average called the Norland mean NP. The Norland mean is regular, linear, and stable. Moreover, any two Norland means are consistent. Cesaro summation. The most significant of the Norland means are the Cesaro sums. Here, if we define the sequence pk by then the Cesaro sum ck is defined by ck equals n. Cesaro sums are Norland means if k 0, and hence irregular, linear, stable, and consistent. CO is ordinary summation, and C1 is ordinary Cesaro summation. Cesaro sums have the property that if h greater than k, then ch is stronger than ck. Abelian means. Suppose lambda equals lambda 0, lambda 1, lambda 2 is a strictly increasing sequence tending towards infinity, and that lambda 0, 0, suppose converges for all real numbers x greater than 0, then the abelian mean A lambda is defined as more generally. If the series for f only converges for large x but can be analytically continued to all positive real x, then one can still define the sum of the divergent series by the limit above. A series of this type is known as a generalized Dirichlet series in applications to physics. This is known as the method of heat kernel regularization. Abelian means are regular and linear, but not stable and not always consistent between different choices of lambda. However, some special cases are very important summation methods. Abel summation. If lambda n equals n, then we obtain the method of Abel summation. Here where z equals exp, then the limit of f as x approaches 0 through positive rails is the limit of the power series for f as z approaches 1 from below through positive rails. And the Abel sum A is defined as Abel summation is interesting in part because it is consistent with but more powerful than Cesaro summation. Equals ck whenever the latter is defined. The Abel sum is therefore regular, linear, stable, and consistent with Cesaro summation. Lindelof summation. If lambda n equals n log, then we have then L. The Lindelof sum is the limit of f as x goes to 0. The Lindelof sum is a powerful method when applied to power series among other applications, summing power series in the Mittag-Leffler star. If G is analytic in a disk around 0, and hence has a Maclaurin series G with a positive radius of convergence, then L equals G in the Mittag-Leffler star. Moreover, convergence to G is uniform on compact subsets of the star. Analytic continuation. Several summation methods involve taking the value of an analytic continuation of a function, Analytic continuation of power series. If sigma ANXN converges for small complex x and can be analytically continued along sim path from x equals 0 to the point x equals 1, then the sum of the series can be defined to be the value at x equals 1. This value may depend on the choice of path. Euler summation. Euler summation is essentially an explicit form of analytic continuation. If a power series converges for small complex z and can be analytically continued to the open disk with diameter from -1 to 1 and is continuous at 1, then its value it is called the Euler or sum of the series A0 plus. Euler used it before analytic continuation was defined in general, and gave explicit formulas for the power series of the analytic continuation. The operation of Euler summation can be repeated several times, and this is essentially equivalent to taking an analytic continuation of a power series to the point z equals 1. Analytic continuation of Dirichlet series. This method defines the sum of a series to be the value of the analytic continuation of the Dirichlet series at s equals 0. If this exists and is unique, this method is sometimes confused with zeta function regularization. Zeta function regularization. If the series converges for large real S and can be analytically continued along the real line to S equals -1, then its value at S equals -1 is called the zeta regularized sum of the series A1 plus A2 plus. Zeta function regularization is nonlinear. In applications, the numbers I are sometimes the eigenvalues of a self-adjoint operator A with compact resolvent, and F is then the trace of A minus S. For example, if A has eigenvalues 1, 2, 3, then F is the Riemann zeta function, zeta, whose value at S equals -1 is -1/12. Assigning a value to the divergent series is 1 plus 2 plus 3 plus 4 plus. Other values of S can also be used to assign values for the divergent sums. Zeta equals 1 plus 1 plus 1 plus equals -1/2. Zeta equals 1 plus 4 plus 9 plus equals 0, and in general, where bk is a Bernoulli number, integral function means. If j equals sigma pnxn is an integral function, then the j sum of the series A0 plus is defined to be if this limit exists. There is a variation of this method where the series for j has a finite radius of convergence r and diverges at x equals r. In this case, one defines the sum as above, except taking the limit as x tends to r rather than infinity. Borel summation. In the special case when j equals x, this gives one form of Borel summation. Valeron's method. Valeron's method is a generalization of Borel summation to certain more general integral functions j. Vallian showed that under certain conditions it is equivalent to defining the sum of a series as where h is the second derivative of g and c equals e minus g. Moment methods. Suppose that d mu is a measure on the real line such that all the moments are finite. If A0 plus A1 plus is a series such that converges for all x in the support of mu, then the sum of the series is defined to be the value of the integral if it is defined. Borel summation. For example, if d mu equals e minus x dx for positive x and 0 for negative x, then mu n equals n, and this gives one version of Borel summation, where the value of a sum is given by there is a generalization of this depending on a variable alpha, called the sum, where the sum of a series A0 plus is defined to be if this integral exists. A further generalization is to replace the sum under the integral by its analytic continuation from small t. Miscellaneous methods. Hausdorff transformations. Hardy. Holder summation. Hutton's method. In 1812, Hutton introduced a method of summing divergent series by starting with the sequence of partial sums, and repeated applying the operation of replacing a sequence S0, S1, by the sequence of averages 2, 2, and then taking the limit. Ingham summability. The series A1 plus is called Ingham summable to S if Albertingham showed that if delta is any positive number, then summability implies Ingham summability, and Ingham summability implies summability. Hardy. Lambert's summability. The series A1 plus is called Lambert's summable to S if a series is summable for any k, then it is Lambert's summable to the same value, and if a series is Lambert's summable, then it is Abel summable to the same value. Hardy. Leroy summation. The series A0 plus is called Leroy summable to S if Hardy-Mittag-Leffler summation. The series A0 plus is called Mittag-Leffler summable to S if Hardy-Ramanujan summation. Ramanujan summation is a method of assigning a value to divergent series used by Ramanujan and based on the Euler-Maclaurin summation formula. The Ramanujan sum of a series F plus depends not only on the values of f at integers, but also on values of the function f at non-integral points. So it is not really a summation method in the sense of this article. Riemann summability. The series A1 plus is called summable to S if Hardy. The series A1 plus is called R2 summable to S if Ries means if lambda and form an increasing sequence of real numbers, and then the Ries sum of the series A0 plus is defined to be Val-Poisson summability. The series A1 plus is called VP summable to S if Hardy.